Hello, and welcome back. Uh, I thought about not streaming today because I already did a DMOJ contest. It was it's gonna be slow. I did the DMOJ and Animal Contest 5. And I don't know. Now it's pretty late because then I wasted some time. But here's how I did on that. I got 1, 2, 3, and 5. It's supposed to be a 3-hour contest, but I started when there was only 2.5 hours left. Otherwise, I maybe could have got problem 4 too. But I decided I don't want to do another virtual contest. So I'll just do some CSES problems. Here's the CSES additional section. And then I'll just start from the first problem that I haven't done. As you can see, I've already done a decent amount of problems. Most of them, the other ones I haven't done, are probably boring. I had done all of them, but then they added new ones. But anyway, I'll just do the additional problems. So let's see, the strongly connected edges. Oh yeah, I already read this one. I'll say my thoughts on it. So basically, you're given an undirected graph, and you want to direct the edges so that it is strongly connected, which means that from every node, there's a path from that node to every other node. So here's an example. Let's say you have the undirected graph that looks like this. If you direct the edges so they're like this, now from here, from every node, there's a path to every other node. Like from here, you can reach all the other nodes like this. It doesn't have to be in a single path. Like here, you can reach this node, and then you can also reach this node. So as you can see, this is strongly connected. So my thought on this is, imagine any strongly connected component. Well, because there's a path from one vertex to every other vertex, there's always going to be a tree, where if you take out the cycles and only start from that, there will be a tree to reach every other vertex, right? So then, what we can do is we can just take our undirected graph and just do a DFS tree, which is just like we start DFSing, and every time we go down, we direct the edge to go downward. But then if we're DFSing, there's an edge that's going back up to a node we already visited. Then we just direct that node that edge going upward. And then at the end, all we have to do is test if it's strongly connected. You could just run like Kosara Juice or any other strongly connected algorithm, but instead, even easier, you can do something like the normal biconnected component algorithm, where you hold at each node, what's the farthest up a node reaches? Either that node or one of its children. This is like the back edge. Like imagine this is a tree. This edge is reaching back here. So you can think of these as the direct down in the tree. Then this one would be a back edge. So you say, what's the farthest up the back edge is in any one of its children? And if it's not as far up as if it doesn't go above itself and it's not the root, that means it's not strongly connected, because that means if you start from here, you can never go outside of this subtree. So then I'll code it and it'll make more sense after I do that. And I think this should work. Let's see. Alright, let's see. So we start out with the input, the edges. Oh wait, we need a number of edges. So I'm going to do the edges a little bit differently, you'll see. So I'm reading in the edges. So I'm going to read the edges into this array, 0 index them, and then for both the nodes, I'm going to put the edge index into the array list instead of the node it connects to. So then that way we can have print them out in order. I would guess to do that 0, 8 of them. And then so then when we're DFSing the tree, oh wait, I'm gonna have to this one. So when we're DFSing the tree, we're gonna change. We can swap AI and BI to change the direction that the node is that the edge is directed in. So then that is why we're doing it like this, and you'll see the links in the code. So then also need that thing I talked about. Let's see, what do we need? So we start out with f of c, but we need the we do f of c is equal to d of c. So d is going to be the distance, and f is going to be the farthest distance reached up by a back edge. How we do it? So p, which normally holds the parent node, is instead going to hold the parent edge if I is not equal to p. Now let's get the node it's connected to. So here, you can see that. So either AI or BI will be equal to C, the current node, but not both. So then we will XOR out, but the one that's equal will cancel out with the C, leaving the other node that it's going to. Oh, we also need to put a visitor tag. This is has the node been visiting? Let me say, so has if not v of x, then we can DFS x and I, and then make f of c is equal to max of c of x. Else we have to do say f of c. Oh, we also have to do first. We have to set the distance of the child node is equal to the current distance plus 1. Then we DFS it, and now we update our max value reached by any child node to be max of what it is and the child max. Then we do a f of c max of. Oh, this should be min actually. Min of f of c comma dx. So here the x node is already visited. Oh wait, there's one more. Let me put this inside the brackets. I also forgot we have to direct the edge to go downward. So we say here we need to make sure that the bi is pointing towards x. So if a of I is not equal to c, swap a of I bi. At the end, actually, let's return to c. Make it a hint. And do. Then you can do FC's one. Okay, like this. Otherwise, we do f of c is equal to min of f of c d of x. Because x is already visited, so it must be a node above. Because if it wasn't visited, then we could DFS downward into it. Right. Yes. Oh wait, shouldn't it always be if a of I is not equal to c? When do we not direct the edge? It's only if it's the parent node. We don't want to redirect it, right? The parent. Hold on, let me think. Well, oh wait, you'll be visiting this node here and also here, right? So you need to say, when you go back up and you hit this edge, you don't want to redirect it again. So you do if d of x is less than d of c. Well, we can just put this here, right? Else if d of x is less than d of ac, if a of I is not equal to c, swap I and d of I, and we do f of c is equal to min of f of c d of x. And now, if p is not equal to -1, that means we're not at the root, and f of c is equal to d of c. That means we're stuck in this subtree. So we should see out impossible. Then okay, actually, I'm gonna do something else. This is just like an implementation choice. Instead, what I'm gonna do is this. I'm gonna hold a bool. This will be the return value, which will say, is it strongly connected? So here, we'll say ret and equals dfs x of I, and then f of c is equal to min of f of c comma f of x. Well, let's do this. Now at the end, we just do ret and equals what? Not p of c, or f of c is less than d of c. So then, if any of these conditions are false, so the reason we're anding is we need all this to be true for every single node, right? P or f of c is strictly less than d of c. Now we can just do if not, we'll do if dfs blah blah blah. So if the return value is 1 or true, then we can print out our edges. Otherwise, it is impossible. Hopefully that all made sense. I don't think it's very... I'm not 100% sure my idea is right, but I think it probably is. OMG. Well, that's not good. Oh, no. 1, 2. 1, 3. 2, 3. Uh-oh. Wait, no. It should be right. What do we do wrong? V of c. Y is not equal to p. C, x or a by x or u. Because either it's the root or f of c is less than d of c. Okay, now we just save this. Oh, that's my Spanish. Let's see, it should be here, where is it, CSES, here, additional problems, and then we do strongly connected edges, that's it. Right, now we just submit it. These will be slow. Look. And this should probably work, hopefully. Oh. It did not work. Huh. We incorrectly oh, wait, I know the problem. Well, I know the problem for those. I don't know the problem for this. For here, we need to make this actually large enough to fit all the edges, so it should be 200,000. But, yeah. But what is wrong with this? See? Alright, I'm just debugging this by printing it out and seeing how it is going wrong. I see. It's not even oh, duh. We also need to make sure that it's actually reaching every edge. Okay, let's do this instead. Make this an int, and we count the number of good nodes there are. Now, there have to be all, so either the whole graph won't be connected, in which case there will be less than n, or one of the nodes will not meet this condition, and then it'll be less than n. So now this should work. Yep, okay. Alright, those were both that and like changing the array bounds, easy fixes. And now let's try submitting. And I think that this will work, probably. Alright, yeah, good. Okay, now we're done with this problem. Let's look at the next one. I don't know if I've seen this. Given an under, your task is to choose the direction for each edge, so that in the resulting directed graph, each node has an even out degree. I see. Out degree is the number of edges coming out of that node. Interesting. Yeah, I don't think I've seen this before. So let's think about it, I guess. So set up a new code. We want even out degree. There are no solutions. Right, only impossible. Right, so hidden. Okay. We'll have like, my stylus has been having problems lately. Okay. Good. Oh, I forgot to turn on music. I felt like something was missing. What do I want to be? Let's do jazz, jazz. Late night jazz, let's just do that. As it is currently 2:07 a.m. for me, late night jazz seems fitting. Okay. So we have a graph that is connected. And see, for this, an example would be if we directed the edges like this. Now both of these have out degree 2 because they have 2 edges facing out. And both of these have out degree 0 because they have 2 edges facing in and 0 facing out. And that will get the out degree even like we want. How do we ensure there's always a solution? This one seems harder than the last one. Like, imagine if you have this. There's no solution here, right? What if you have, like, this? Here there's a solution, because you just face them both like this. What if you had an extra edge here? Now there's no solution. How would we know that this has a solution and this doesn't? Well, we know describe the direction of the edges. Okay. Think of ideas. What are your ideas? Nothing is immediately coming to mind for me. So I know we want the out directed. Doesn't mean. Is there like another way we can say what it means to have a even out degree? If it has even out degree. Even out degree. Assume the graph is simple. Okay. Yeah, I'm definitely... Alright. Well, okay, let's mark every node by how many edges are coming out. So if so like if a node has an even number of edges connected to it, that means it will need the same amount of edges going in and out, right? But if it has an odd number, like there's like 3, it'd have to have an odd number of edges going out but an even going in. What does that tell us? Well, think about what do we want to think about? Connect to even. If we add an edge between two even, we can think of it as like a only print impossible. Let me look at the next problem, and then we'll come back to this. Find the middle element when the numbers in an n by n multiplication table are sorted in increasing order. Interesting. My friend, one of my friends told me a similar problem to this, which was in like an n by n multiplication table, how many distinct values are there? However, I was never able to figure it out. I guess the typical way to do something like this is you need a function. I'm guessing it's going to be binary search, right? And you're going to end up doing a function like f of x is equal to number pairs multiply number pairs x comma y such that x times y less than or equal to z, like this. And then you're just gonna binary search until you get like half the pairs or less than it. Alright, so let's say we have a fixed z. How are we gonna count the number of those pairs? Well, oh wait, that's easy, right? We can literally just iterate through. We can iterate through all the numbers from 1 to 10 to the 6th, and then see how many of the others like pair with it. We'll make it like less than z, right? And that'll just be like n log would be like n squared, but that's just on log n. Because the function takes on time and the binary search adds a log n. Okay, that seems really easy. I'll implement this after thinking about this a bit more. Even. What does it mean for it to be even? Even out degree. So like, what I'm thinking of is like, you know, when like the total degree is even, we want the out degree to be even. That means we want the in degree to be, well, not equal to the out degree. I don't know, it's making me think of like an Euler tour, but I don't think it's gonna be like that. Imagine you say every node starts out equal to its degree, but when you direct an edge, the one you direct it towards subtracts 1. What is your goal then? You want, from there, doing that operation, you want to make all the numbers even, right? After you've directed every edge. So, start out with like a 2, 2, 3, 1. And how do you know strategy to make them all even. We know that, well, first off, this 1 needs to become 0, right? So you subtract 1, make this 0. And you add this, so 1, that becomes 2. Well, I guess then there's no solution, right? What if we did this? And then, hold on, there was a solution here, right? Then we do this, subtract 1, this, subtract 1. Okay. I'm not really sure how, well, that's the exact same problem, so thinking about like that isn't really helping me. Any new ideas? Out degree even, out degree even, out degree even. Because you could just say the same thing as they all start from 0. When you direct an edge, it adds the not the way it's facing, add 1. But what is the condition for that it has a solution? Let's think about that first, right? Good to usually think about what the conditions are such that a solution exists. So in this example, we had 2, 2, 3, 1. How do we know there's a solution here? Well, in this connected component, first off, we can solve each connected component completely separate, independent, right? Now, I think, based on the examples I've done, if the sum of degrees is, so first off, the sum of degrees will be even, right? Because each edge will be counted for the degree of 2 different nodes. But if the sum of degrees over 2 is even, then I think it's possible, otherwise it's not. So here you can see the total sum is 3 plus 1 is 4, plus 4 is 8. 8 divided by 2 is 4, which is even. You can see here, if we have just one edge, then the sum of degrees is 2. And then you divide by 2, it's 1. That's odd. But like if you add another edge, and it's like 1, 2, 1. Well, basically that just means that every component has a even number of edges, I guess. Because here you can see an easy example as you direct them like this. Right. So, let's say we assumed this idea was right. How would that help us then? The number of edges in the component is even. Think about you have like a what was I gonna say? Think about you have a tree. Let's solve this on a tree first. So for solving this on a tree, we know that for every leaf, you have to direct it upward, right? oh wait. On a leaf, you have to direct it up. No. On a leaf, you have to direct it downward. And now, based on the number of children, look at the node above. You see, is it currently even or odd? In that case, we direct the parent accordingly, right? So for a tree, we can just keep doing that, and then on the top node, we know doesn't have to be set. So now, let's create a, now, let's do the same thing, but like before, there can be some like back edges from like the repeated node, from like an edge that goes to one we already visited. How do we deal with those? I'm thinking we do this. We always direct them going upward, and then we do the same algorithm. Why? So that way, they'll only affect like the current node in the DFS. So that means parent will only be dependent on its children still, right? Because like, imagine if you waited to direct it like this. Well, I guess it wouldn't really matter. No, we're just gonna... Actually, I think it doesn't even matter. I think we can direct it arbitrarily. Now, then we run the same algorithm. And how do we know that, like, no matter which way we direct those back edges, the root will always have a solution if it exists? Well, we know that imagine this was facing upward, but we flipped it going downward, right? Then we'd have to propagate, like flipping these upward, and it'd still end up the same, right? I think I'm gonna guess and say that this idea works. Let's try coding it and hope that it works. So it'll be a little bit similar code to the last problem. So once again, we need to make this the size of the M because we're going to do the same thing as before. Or we can hold the edges like this. V should be G. So now we read the sizes, read the edges. Zero index them. We put the node index into the graph adjacency list for the node. Now we're gonna have to DFS on each component, right? So we'll iterate through all the nodes and say if they're not visited, let's DFS it. And let's have the DFS return does this edge need to be directed up or down, which is basically just like the parity of the nodes. So if we say that the quote-unquote parent edge needs to be directed up, well, there is no parent edge, so it can't be directed up, so we'll say it's impossible. So we'll have like a rect 1, and then rect and equals, not DFS. And if rect, now in the DFS we'll have directed all our edges. So I'll print them out. Otherwise, it's impossible. Right now, let's go to the DFS. It'll be pretty similar to before. So market is visited. Iterate through. Is not equal to P. And let's hold like the parity thing I said. Remember, we need to return it. So then, first in X equals V of I. V of I, let's order. Now let's see. Give I. So first, now we say if DFS X, I. So if this is corrected, we say if I else. So we need if here we need to direct it towards B. So if A of I is equal to C, so I A of I, else if A of I is not equal to C, so we should be pointing downward. Oh wait, we need to test if it's visible, right? If not B of X, okay, what do we do? Alright, I'm gonna do a little trick where before we were like testing the distance to see if it was like going upward or downward, right? Like to see if like we are looking at the edge this way or from this node. Instead, we're gonna set V of C equal to -1. See, but then when we return from this section, then we set it equal to 1. What does this do? Well, so we know that when we haven't returned from a node, V of C is equal to -1, right? So imagine you mark this node as -1, and then you go down. When you look at this edge going up, V of C will be -1. Then you'll finish DFSing from this node, and then go back up, and then now here will be 1. So now we see that this will be 1. So all we have to do is not X. We say if I is equal to C, swap if I and V of I. Oh, and then because we have red X or equals 1. DFS XI. Let's do this. Let's do it like this. If so first off we do if we need it like this. If not v of x, if d of s xi, a of I is equal to c. I don't like it looking like this. Alright, if d of s I push. Not equal to. Alright, there we go. So, we know that if alright, this should be not. So we know that if so when dfs xi is equal to 1, that means we wanna, what do we wanna do? That means we need this edge that's like going towards x to be pointing upwards, which means that a of I should not be equal to c, right? Because b of I should be equal to c. So if they're not equal, then we swap them. Otherwise, if this is 0, that means it should be pointing downward. So it'll be 0. So a of I should be equal to c. So if it's not equal to c, then they're not equal. Hopefully that makes sense. It's a bit messy, but whatever. Like this. In case you haven't noticed, I care probably a bit too much about the aesthetic of my code. No way. I need to update red based on this, right? Okay, if dfs xi, that means we do what? Plus a of I c. Always need to do red x equals 1, so this means it's facing downward. Otherwise we do alright, I think it should be like this. Will this be right? It's like 2, 1, 2, 3. Alright, yeah. It's all the opposite order of this, which I think will be fine. Hopefully. We need to do new file. What is this one called? This one is called even out degree edges. Let's see, did we do it right? Maybe we did these wrong. We need to flip it around. Oh, where is it? I think we got it though. Hopefully. Oop, we did not get it. Huh. What happened here? Oh, wait. First off, here, that should always XOR 1. Then here. Alright, let's try it again. Hopefully this fixes it. Let's see. We submit. And let's go. Alright. So we got this one. Nice, nice. We got all the bots watching. I always enjoy that. And then, let's go to the multiplication table. Oh, we said this one was easy. I already talked about it. It was the binary search. So let's just quickly code that. Alright, so let's see. Let's get a template down. Put it down. And now, let's start coding. So maxim is 6, right? Let's see. So here's our, like, f function. Right, and we see n. 0. We're gonna make another thing, m. We're gonna say m is equal to n times n. Equals 0, y is equal to m, well, m is 0 is equal to 1. Mid, this is just putting a typical binary search. We say if f of mid. So if the number of pairs that multiply up to mid is so what, less than less than m over 2. Since what did we need? We need the median, right? Yeah. It's less than m over 2. So we want the highest value. Let's do it. It's greater than mid. We set r equal to this. Else we set l equal to this. Well, that's just the same as okay. But if we do it like this, l is less than it. No, we need to do it like this. And then we see our r. Right, because l will be the highest value that the number of pairs is less than m for 2. So when you add value r, which is just l plus 1, right, based on this condition, then that will be the value we need. Am I doing this right? 3 times 3 is 9. 9 over 2 floor is 4. 2, 3, 4. So here we'd have 3 pairs, and here we'd have 5. We have 4. Well, let's should be this one. Assume n is odd. Okay. N is odd just to ensure that there's an exact middle, right? And not like an even number total. And this one is 10. Over 2 is 5. So less than 5. Okay, this should be right. Now we just make the f function. Now this is where, like I said, we just iterate from I 1 to n and say, right, this equals min of n x over I. this is just counting like how many values it can pair with such that it's less than or equal to x. Oops, let's see. I think this is all it is. Let's see. 3. Yep. And that is an easy clap task. Easy, easy, easy. Will it work? I think it will, but not 100% sure. Hopefully this works. Multiplication table. Alright, nice, nice, nice. Did work. Now we'll move on to the next one I haven't done. Special substring. Substring is called special if every character that appears in the string is the same number of times in the substring. Every character appears in the string. See, so like here, all the characters from A to Z appear. And here they appear the same number of times, blah, blah. I see. So what does that mean? So imagine looking at the prefix sum for each of these separately. Well, like, if we look at we need the prefix sums where, let's look at this string, A, B, C, C, A, B, A, B. Now, let's look at, for each of the characters, what is the prefix sum? So they all like start out as 0, right? And then this one, 1, 0, 0. This becomes 1, 1, 1, 1, 1, 0. So each of these rows is like the sum of the number of times A has appeared up to that index, or B has appeared up to that index. Hopefully you get that. 1, and then 1, 1, 2, 2, 1, 2, 2, 2, 2, and then 3, 2, 2, and then 3, 3, 2. Alright, now basically, if we think about it like this, we're counting the number of times where, so like when you take, so imagine this pair, right? That would represent the substring right here, because it's like the prefix sum up to here minus the ones before here. And we can see this substring works, right? There's 2 A's, 2 C's, and 2 B's. Why? Because we know that for every single one of these values, minus every single one of these gives the same thing. 3 minus 1 is 2, 2 minus 0 is 2, and 2 minus 0 is 2. And then, okay, yeah, I've seen this trick before. So now we need to count the number of pairs that like are the same, right? Well, here's what you can do. Instead of storing all the prefix sums for the first value, instead so like you look at the prefix sum for one of them, let's say A minus B and C. So like the prefix sum of B, let's say the prefix sum of B minus A, the prefix sum of C minus A. In that case, it'll be like here it's like A minus A is 0, B minus A is -1, C minus A is -1, and here it's just 2 minus 3. Here you can see it's the exact same thing. So all that matters are these differences between one of them are all the same, which is why. So now it becomes a much easier problem, which is just counting the number of these groups that are the same. There's a old USA code problem in like 2012 or 2013 that had that. Do I even want to code this? It's pretty boring. Whatever. I'll code it. So we're gonna use an array. So we're gonna say k is the size of the alphabet, which is 26. Since there are 26 letters in the alphabet. And we say def array k. And then we are gonna store a map to store each of these little difference arrays, so we can count how many pairs go with each. T int. Oops, let's call it f. Now let's see. Oh wait. And string s. Now we just first off, we need to see which characters appear at all, right? No. Wait, let's just make it T A V. So first off, V will say, does the character exist at all? Of 0 plus let's say v of s of I minus a little 1. Now we're gonna set m to the first character that actually exists. And we're gonna find b begin count 1 begin. Now we're gonna iterate this one again. And let's say fa. So A is going to start out with all zeros in it. Also, we can just iterate like this instead. 5. S. Now, if int x equal to I is A. Actually, let's just do this. So here, we're gonna just subtract A from all the chars too. So now, instead of thinking as S as a string, you can just think of it as an array. So now we say if I equals M. So if I is equal to M, that means we have to change the difference of everything else to be. Right, imagine when we increase M, A, means we have to subtract 1 from everything else. But we have to keep A 0. We do B of J, A of J, else. Else we just do A of add one, we subtract here. Otherwise, we just do a of I is plus. So each of these minus the number of a. I'm inverting it. So instead of being like this minus a, I'm doing a minus. No. I want to do this minus a.
Why does it seem so inviting?
Well, remember, we're also not supposed to change a. Oh, okay, let's just do b of.
It spells the thrill of first lighting.
We're gonna change the first instance of v to be equal to 0 instead. So why are we doing that? Now we say if not v of I. Else. Let's switch it. Okay, now we just do. We also need a total ret value. And we just do ret is equals f of a and f of a is plus. So this will be counting how many times did like this difference array appear before, and we add one to a. Now we can see. And this should probably work, as long as I didn't do anything stupid. And I did something stupid. What was that?
Dreamers with empty hands may sigh.
What'd I do?
It's autumn in New York. It's good to
What did I do? Say Alright, so I'm looking at the difference array at each index. What the? Well, that seems like a problem. How is this 24 and 48? Huh? How is this becoming 24?
It's autumn in New York that brings the promise of new love. Often mingle with pain.
0. 1, 2, 2. Huh.
Lovers that bless the dark.
I don't get it. Where am I messing up?
On benches in Central Park. It's autumn in It's
why is this becoming 24? What? That makes no sense. Started out as 0, 0, 0. And then just from these lines, it has to be 24. So we know that just from this line, it has somehow become negative 24. Wait, oh. Okay, I do need to do it like this. This is why you should probably be using brackets always. But, oh well. Okay, now it should work. Yeah, easy clap. Now let's see, special substring. Special substring. Do. Alright, easy permutation inversion. Your task is to count the number of permutations have exactly k inversions. This was also from a US Psycho problem too, right? You could do this with generating functions. Let's see if I can remember how to do it correctly. How long has it been? It's only been like an hour. Foo-foo, Tim. Alright, what am I doing? Oh, this is boring. I don't know if I want to do this one. Inverse inversions. Tasks create inversion. Has exactly k inversions. You want with n. How many inversions? Oh, this is easy. Task to create is longest monotone subsequence has exactly k elements. Longest monotone subsequence. 2, 4, 5, 4, 3. I see. I think the longest monotone subsequence is at least square root of n. And then it's pretty easy to go from there. I think I might just go to bed. All these problems. All these next ones look pretty boring. I know I've seen ones at the end of the additional section that looked interesting, that I haven't done. You have n coins, each of which has a distinct weight, 2 stacks, Going to a stack. Determine which stack is heavier, huh? What? Weird. How do we know which is heavier? So basically, you have two stacks. Like a stack 1. My stacks. Oh. I think, I don't know. It's 3 a.m. now, and I'm tired. So I think I'm just gonna go to bed. I also have to do English reading in the morning. So I should probably go to bed. Other boxes. Yeah, okay. I'm done for today. What's that? I guess that's it. Adios.